strange.
And the semi-tube parked alongside the road getting food somewhere. I don't know.
This first one, I know we talked about it already, but what was it? Thomson's discovery? Okay. The existence of an electron and that the electron can leave. Oh, there's one more thing.
And that's charged.
The electron is charged. Okay. Rutherford?
Densely packed core.
Okay. That core is positively charged, which is the opposite charge that the electron has, right? Yeah. Alrighty. So what did Sadi figure out about the atom?
The proton is way more massive than the electron.
That instead of having just one chunk of positiveness that's in the nucleus, that it's composed of individual protons. So when Rutherford discovered that there was a nucleus, he didn't discover that there were protons. He just discovered that all the mass was tightly packed down into that dense little core. But he didn't know that there were individual protons that were composing that positiveness. Chadwick? Okay. How about Bohr?
The first model of atom that you use in the solar system to make or design. The planetary model.
So he came up with that first model of the where the electrons are located around the atom, and it was the solar system model. It's helpful to think about. It's not good enough for us to continue using it, but sometimes it's nice to visualize. It's easier to visualize something like that. And how about Heisenberg?
He had a more accurate model using mathematics and statistics.
Sure.
And he came up with a new science.
Yeah. Okay, so he used the mathematical statistical model, basically just determining where the electrons would probably be located. And doing that again and again and again, the probability of where you would find them became pretty apparent. It was like, oh, they're usually found here or here or here. And derived from quantum mechanics. When you're measuring a temperature substance, what are you measuring? Okay. I like just speed, right? Yes, you're right. temperature is a measure of the average kinetic energy of an object, but I'm not exactly measuring its mass. Kinetic energy is 1/2 the mass times the velocity squared. If you're sitting there and your temperature goes up, is it because your mass went up? Probably not. It's because your molecules are moving faster, right? So when I'm measuring something's temperature, in essence, I'm really just measuring the speed at which the molecules are moving. Isotope. All right, it's an atom with a set number of neutrons. Example would be carbon-14. Example would be hydrogen-2. So the atom is what it is because of its number of protons. And if I vary the number of neutrons, then I'm talking about various isotopes of the same element. Allotrope?
Different structural combinations of atoms.
It's specific that it's the same atoms.
It's the same element.
It's the atom bonded to itself.
Diamond is an allotrope of carbon. Ozone is an allotrope of oxygen. So can have varied forms of those atoms hooking up with themselves. It's basically like I hand you a bunch of the exact same red six nubbed Legos. What can you make with them? Different stuff. So I give you several carbon atoms, and what can you make with them? We know of about 4 things. The buckyball, they don't do anything but sit there by themselves, or the diamond or the graphite. And the diatomics?
It's atoms that are always found connected to something else.
Nope.
And so
It's 2 atoms of the same
Same
element
element.
stuck together. Are they always
So-
bound naturally?
They're always bound together with themselves. So if I'm looking for a specific element, just one element of fluorine, I will never find myself any F. Doesn't exist. It only comes in F2. Can I get a fluorine by itself? Get one fluorine atom? Sure. HF is a molecule, but I'm not talking about the element anymore. I'm talking about a molecule. So when we're talking about the diatomics, we're talking about an element in its pure elemental form, and there are 7 of those elements on the periodic table that can never be found by themselves. And so those were hydrogen, nitrogen,
Oxygen, fluorine.
so they'll always be paired. Pure chlorine is Cl2. Alrighty, atomic number for beryllium.
why did it take 33 years?
Oh, sorry. Why did it take 33 years?
No one was looking
Nobody
for
was.
it.
No one looking. Because they already found the positive and the negative, so why would they find the neutral? And it has no charge. So an electric field, positives and negatives, and magnets don't affect it. So when they were doing all these things with magnets and positive and negative charges, the neutrons were just hanging out. They weren't affected, so they didn't notice anything.
Was it also because their technology wasn't up to par? I mean, they knew that there's a mass missing, didn't they?
No, they
I thought
didn't.
that's what it said.
Well, that's what Chadwick was like, hey, there's a problem with the masses here.
That's only because he developed superscales.
Yeah, but it was him. It was the guy who discovered the neutron that realized that there was a mass differential. They and when he pointed it out to everybody, they didn't think it was a big deal. They thought it was just inconsistencies with the measuring men or inconsistencies with the equipment. It really is, they weren't looking for the thing. So nobody decided to build, I mean, we know what the mass of an electron is. that is a ridiculously tiny particle. And we figured that a very long time ago using this oil drop method. But somebody designed that. So when somebody decided we should figure out what the mass of an electron is, somebody came up with a piece of equipment. So I'm usually not concerned that it's a technology thing, because if somebody wants to know badly enough, then somebody will figure some way to measure that device out. So atomic number?
4.
Electrons? And then this is beryllium for and then 82. What is that? PB, which is lead. So 82 protons, 82 electrons, and so 207 minus 82, what we got there? 125. That looks good. Okay. Osmium. Okay. What element is osmium? So if it's element number 76, 76 protons, 76 electrons, and 76 and 190, so 114. Thanks. And radium is Ra, and it's element number 80. So it has 88 electrons, and if it's this particular isotope is 138 neutrons, then I'm at 100 or 226. Okay. We didn't do this, but how would you write the isotopes for each one of those 4 atoms? BE 10, PB 207, OS 190, and RA 226. How come I don't need to include the number of protons with that?
Because it doesn't change.
More.
If it was a different proton, it'd be a different atom.
So the symbol is basically telling me the number of protons, right? So it says BE, so immediately that means what?
4.
4 electrons. You don't have to tell me 4 electrons. You told me 4 protons already. When you said BE, you said 4 protons. They are synonymous with each other. So if the total thing has a mass of 10, then I just subtract off that 4, and that tells me there are 6 neutrons. Okay.